Hi, I am Prasanna from Georgia Institute of Technology. Today I will talk about visualizing ferroelectric switching in plan view with nanoscale resolution and the interesting insight that this level of spatial resolution enables us to draw. The results presented today were collected by electron beam induced current (EBIC) imaging performed using a scanning transmission electron microscope in Professor Kruzregen's group at UCLA. Polycrystallinity in hafnium-based ferroelectric films drives massive device-to-device variation and has been known to be a significant bottleneck to areal scaling in hafnia-based ferroelectrics. Most ferroelectric characterization is still performed on devices that are tens of microns in size. At these dimensions, the response is an average of thousands of domains, masking the nanoscale switching that ultimately limits scaling. While prior electrical studies have inferred single-domain switching from indirect measurements on scaled FEFETs, direct nanoscopic confirmation has been extremely limited. This leaves several foundational questions unanswered. What are the grains and what are electrical domains? How does a single domain switch? How do domain size and geometry influence coercive fields and switching speed? And critically, can variations in nanoscale switching kinetics be harnessed for multibit operation? Answering these questions requires spatially resolved measurements of polarization switching at the atomic scale. This is exactly what STEM-EBIC enables us to do. Before we go into the experimental setup and the further details, let me clarify some terminology. In this talk, I will use the term domains to refer to electrical domains. Here we define an electrical domain as a contiguous set of dipoles that switch at the same applied field and pulse width. This is an experimentally observable definition enabled uniquely by EBIC, which provides localized polarization response at nanometer scale resolution. The samples for STEM-EBIC are fabricated on a 20 nanometer silicon nitride membrane window. The window is supported by a 200 micrometer thick silicon substrate that serves as the window's frame. On the substrates, an electron transparent bottom electrode, tantalum nitride in this case, is sputtered, followed by a plasma-enhanced ALD deposition of HZO. Again, a top electrode is deposited on top before the device is annealed at 700 degrees Celsius. EBIC works by rastering an electron beam across a ferroelectric sample through the electron transparent nitride electrodes. This creates electron hole pairs that are deflected to the top and bottom electrodes based on the strength and polarity of the internal electric field, which is proportional to the local ferroelectric polarization, hence enabling us to capture the local polarization. These signals are collected using two transimpedance amplifiers, one for each electrode, and their strengths are used to determine the local polarization across the samples. The Bayesian holder is also used to apply voltage, and the electrical characteristics of the entire sample are measured in situ using standard PUND, positive up, negative down measurements, to study the correlation between electrical polarization and polarization switching and domain evolution. After the sample is set to a polarization state by applying a voltage pulse, the STEM-EBIC image is captured. As mentioned earlier, the charges are captured using two transimpedance amplifiers, one for each electrode. How is this measurement done then? The sample is always reset to one particular state, followed by a set pulse to polarize the ferroelectric thin film to a different polarization state. The EBIC images are collected after each set pulse, and the sample is reset after the EBIC image is collected. This process is repeated with increasing set voltages to obtain the polarization electric field characteristics, or the PE characteristics. The sample in this case is roughly 1 micron cross 1 micron and has over 60,000 pixels, with the pixel size being 4 nanometers cross 4 nanometers, thus giving a high resolution map of ferroelectric switching kinetics within the sample. For the first experiment, we use 17 voltage steps at 300 microsecond pulse widths each. We did this both in the positive and negative direction. Here are the 17 EBIC images captured in the positive and negative direction, with the EBIC signal from 1 pixel shown on the right. These pixel resolved EBIC curves reveal sharp polarization switching, and saturation with no partially polarized states. Multiple pixels can be averaged to derive the PV characteristics of the whole sample. This PV characteristics derived from the EBIC is shown to match the electrically measured PUN characteristics. Now let us look at where in the film the switching actually happens. These are two EBIC images of the same area, one captured with zero applied field just in the reset state with the polarization pointing up, and one after a 3.5 megavolt per centimeter pulse with the polarization pointing down. The contrast reverses because the sign of the local electric field flips. So the difference between the two images tells us directly which parts of the film have switched. Now let's look at a small region within this entire piece. Zoom into this region. At the bottom, we have a remanent field tracker. The remanent field is a measure of the local polarization averaged across the region of interest. Stepping through the applied field, we see that the domains on the right, top right, switch in a single abrupt step with no partial polarized states. This is also reflected by the step increase in remanent field shown in the tracker at the bottom of the screen. Here, domains switch coherently in a single step, suggesting that the switching mechanism is governed by field-driven nucleation events rather than a domain wall creep or domain wall motion, as is common in perovskite ferroelectrics like barium titanate or PCT. The same behavior shows up across different regions on the sample, as we can see here on the left of the sample and again on the left of the sample here. Taken together, these three regions span almost 1 megavolt per centimeter in coercive field, and each of them switches in a single abrupt step. This is what we mean by uncorrelated single domain switching. We also see this in the reverse direction when a negative electric field is applied. The smooth macroscopic loop that we measure typically in a lab is simply a sum of these many sharp independent switching events with a distribution of coercive fields.
For the second set of experiments, we moved to a thinner ferroelectric film, 10 nanometers HZO in this case, with titanium nitride electrodes. And instead of stepping only the voltage, we stepped both the electric field and the pulse width. The field of view in this case is 285 cross 166 nanometers, and we begin from a fully reset state where, as you can see from the blue gradient, all the dipoles are pointing upwards. Now, as we increase the electric field and the pulse width, we see the fraction of dipoles switching and the fraction of red colored regions increasing. Now, if you look at the top right corner, we see that the fraction of switched fraction of the ferroelectric thin film has increased monotonically, and towards the top right, most of the region has become red, meaning most of the ferroelectric thin film is now pointing downwards in ferroelectric polarization. This is a signature of nucleation limited switching, where the field and the time are interchangeable in activating a given region over the energy barrier to switch, and the switched regions appear as discrete patches which switch sharply with no signs of domain growth. We also never observe any partially polarized state throughout the switching process. Now let us look at the switching as a function of a constant electric field, 1.2 megavolt per centimeter in this case. We start with a 0 microsecond pulse and increase the pulse width as we go along. While we do this, we also look at a zoomed in version of the device, roughly 50 nanometers cross 50 nanometer region. We have also superimposed the electric domain boundaries that we had reduced earlier on top of this film. And as you can see, when you go from left to right, as the amount of pulse width, as the pulse width increases, the fraction of switched regions increases, and we can also see that the electric domains switch sharply with no signs of domain wall motion or growth, like we see in perovskite-based ferroelectrics.
We look at the same thing from the perspective of a constant pulse width and increase the electric field, and you will see similar characteristics. Now let us quantify this across three length scales. First, we integrate the polarization across the zoomed in region, which is about 47 nanometers cross 47 nanometers. We obtain smooth gradual curves similar to NLS measurement that is done in the lab. We show the x-axis as the pulse width, and we show polarization switching curves at different electric fields. Now, let's zoom into one particular domain. Now we begin seeing sharp polarization switching without any partially polarized states. Again, the x-axis is pulse width, and the curves are for different electric fields. Now let's zoom into a pixel. Here, a pixel is roughly about half a nanometer cross half a nanometer. This is the smallest ferroelectric unit that has ever been characterized. The switching is just as sharp as we saw even at the domain level. Subdomain resolution here reveals that there are no additional structures inside a domain. It further confirms that there are no partially polarized states even at a sub-nanometer scale. Because we follow individual domains, we can actually fit each one of these domains separately to nucleation limited switching dynamics. Here we fit the switching time to exponential of the square of the inverse field. On the left, we have shown three representative domains with the switching speed fitted to the nucleation limited switching equation that you can see here on the right, and we extracted the activation field for each of these domains and also the characteristic switching time. Repeating this fit for every domain within the field of view, we obtain spatially resolved maps of the activation energy and the characteristic switching time across the entire sample. Both are strongly heterogeneous with the characteristic time spanning more than 10 orders of magnitude across the sample. This is the microscopic origin of wide switching distributions that are normally fitted phenomenologically at the device level when we characterize them electrically. If we look at the sample as a whole, the 285 cross 166 nanometer region, we are able to recover the familiar sample level NLS behavior that we measure in a lab. And we are able to show a good fit across pulse widths from all the way from 100 nanoseconds all the way over to 100 milliseconds, and fields from 1 to 1.4 megavolt per centimeter. The extracted NLS parameters are shown on the left here. From the domain level fits, we can also build phase maps of three different quantities that I would like to point out here. The minimum field required for each of these domains to switch at any pulse width. That is what you see here on the left. In the middle, you see the switching speed at 1.5 megavolt per centimeter. And on the right, you see the remanent polarization. The heterogeneous nature of all these domains and the variation across these domains is evident through all these three different phase maps. Now let's look at the variation of three key properties with the size of these domains. On the left here, we see the remanent polarization. Larger domains seem to have larger remanent polarization. They have about nearly twice the remanent polarization of the smaller domains. And in the middle plot, we show the minimum field required to switch these domains. And we see that larger domains typically require slightly larger electric fields to flip them. That said, contrarily to normal intuition, the switching speeds of these larger domains at 1.5 megavolt per centimeter are also nearly half an order faster than the smaller domains. We can now use these maps to build virtual devices of any size by selecting subregions of the polarization map and treating each one of them as an independent device. At 50 nanometers cross 50 nanometers, the distribution of the two polarization states are well separated. There is no overlap and one-bit operation can be performed robustly. However, when we shrink the device down to 5 nanometers cross 5 nanometers, a tail appears, and this tail comes from the variation in the remanent polarization between the small number of domains that each of these devices contains. And this results in an increased bit error rate. Now we have summarized the variation in polarization across different device sizes. We see that error-free one-bit operation is possible down to 200 nanometer square devices roughly, with the overlap increasing with any further scaling. Plotting the standard deviation of polarization against the device area helps us quantify this, with the variation increasing linearly with the log of the area. This gives a simple experimental scaling rule for predicting variation in polycrystalline HZO. Usually this is obtained, or this sort of a Pilgrim law type rule is obtained from electrical measurements. This is the first ground up deduction of this type of a rule. We can also separate where the variation comes from. There are two variations that I want to talk about. One is inter-domain variation, that is the domain variation between one domain and a different domain. That is roughly about 8 microcoulomb per centimeter square. On the other hand, even within a domain, that is variation, as you can see from the color gradient on the zoomed in domain on the right. This variation, however, is only half the variation that we see across domains. Now let's talk about multibit operation. Conventionally, multibit operation is assumed to arise from partially polarized states in ferroelectrics. By constructing 100 nanometers cross 100 nanometer device maps based on the EBIC maps, we reveal that multibit operation in ferroelectrics arises from statistical distribution of switching characteristics rather than partially polarized states. Now, we have a 100 nanometers cross 100 nanometer region here. That's a zero electric field. At 1.1 volts, we see that the blue regions have switched. When we apply 1.3, the orange regions have switched, and when we apply 1.5, the green regions have switched. Now we have 4 distinct regions that switch at distinct voltages, equally spaced distinct voltages, enabling multibit operation. So now we summarize the distribution of the 4 states across 60,000 devices, showing minimal overlap, indicating the possibility of robust multibit operation, despite variation in the switching kinetics and remanent polarization. The reason this works is because of statistical variation within the 100 nanometers cross 100 nanometer devices. Each 100 nanometer cross 100 nanometer device contains a large number of domains. So the fraction of domains that switch at each of these given fields is reproducible from device to device. This is what keeps the 4 states well separated, and it means multibit operation can be engineered by engineering the distribution of the domain thresholds, even in the absence of partial polarization, as we have established here. One thing to note, however, is that scaling below 100 nanometers cross 100 nanometers will result in loss of the statistical variation that enables this type of multibit operation. To summarize, we have resolved switching behavior of ferroelectrics down to the smallest measured ferroelectric unit, which is half a nanometers cross half a nanometer, and shown experimentally that partially polarized states are absent in polycrystalline HZO down to subdomain dimensions. We have extracted areal scaling loss for polarization from a down-up perspective. We have extracted switching kinetics and variation. We have also shown that multibit operation arises from ensemble domain switching. Together, these insights will hopefully provide an experimental framework for designing scaled, dense, and reliable ferroelectric memory.